Hi, my name is Tejas Kadambi, and this is my presentation of my honors capstone project, which I completed this semester regarding the learning of parametric dynamical systems. This project was done alongside Professor Alex Gordetsky, professor in the aerospace engineering department. So the motivation behind this project was to analyze some data regarding experimental Hall effect ion thrusters generated by PEPL, or the Plasma Dynamics and Electric Propulsion Laboratory. So the data follows a rough model, contains some delay differential equations with different states that are time varying, and it contains some unknown parameters in those equations. So to characterize this model on a general scale, we're looking at something in the form of y equals f of x and theta plus some noise term. And we want to determine theta, which are the unknown parameters, and x would be the input and y would be the data. So this data is what's known as time series data. So the output of the data or of the model is a function of time. And this is what's called, or also known as, a dynamical system. And we wish to learn the dynamics of the system. And these dynamics are governed by the parameters which we are trying to learn. We can characterize what's known as the posterior of these parameters using Bayesian inference, specifically a technique called adaptive Metropolis Hastings Markov chain Monte Carlo. Once you've characterized the posterior, we can analyze it to predict and simulate different conditions and trajectories with some level of uncertainty. And this will be explained and shown in more detail throughout the presentation. So a high-level overview of the overall technique, or Bayesian inference, and the methodology behind it. So what we begin with is what's called a prior, and these are our initial beliefs of the parameters itself. So they might be anywhere on the map, and we just have to start somewhere. From there, we can gather our evidence and compute what's called a likelihood. So given our prior, there is some likelihood of our belief of the evidence appearing a certain way, given our prior. We get the evidence, update our belief, use it with the likelihood, and then compute what's called the posterior, which is our belief after evidence, which is mathematically the sum of the prior and the likelihood. So putting it all together, we have our prior belief, we get our evidence, update our belief, and get our posterior belief. Get more evidence, update our belief again, and get our posterior belief again, and the posterior will slowly shift towards the truth. And this is a high-level overview of what Bayesian inference does. So this particular method of Bayesian inference, called Markov chain Monte Carlo, the first step is to define the probabilistic model, and this represents the posterior of the parameters. So we have a general sense of what the posterior should look like based on our model and the data itself, and there's some model, of course, the data fits, and that is the model that contains these unknown parameters. So we can sample the posteriors using our probabilistic model, and we can sample them randomly with some normal distribution that's centered around some mean and has some covariance for the randomness. And based on the density that these random samples land in the posteriors, we can choose to accept or reject them based on whatever the criteria are. So looking at the sample banana plot above, the highest density regions are located at 0 and close to the origin. So for instance, if our initial sample is somewhere on the banana plot and we randomly sample and our new sample is in the highest density zone, looking at the formula for the acceptance and rejection, we're going to find the minimum of 1 and the ratio of the densities. So if the newer point is in a higher probability region than the older point, the minimum will be 1, which means it's going to be accepted 100% of the time or with certainty. If the new sample is located in the lower density spot, that means that it's going to be accepted with whatever the probability is, which is associated with the ratio of the densities. So what happens is we start with our initial sample and then choose it and then keep randomly sampling maybe 1,000, 10,000, 100,000, a million times, and then generate all these samples, which we can choose whether to move to that new location and store that new sample or stay where we are. And if we stay where we are, the density of the current sample increases. And a distribution is generated after generating all these samples. So you can see what's called a one-dimensional marginal, or our sample distribution of the same banana plot below. And you can see the axes match just how they should and as expected. A histogram shows the density at each spot. And as expected, the density is highest in the middle, close to the origin, which is what we would expect. So a simple variation that we employ of this Metropolis Hastings algorithm is called the adaptive Metropolis. So essentially what it does is it stores every single sample and computes a rolling average. So it updates where the mean is and what the covariance should be to generate the new sample with, because the old samples are generated with the mean being the current sample's location and the covariance of some initial covariance that's an input into the function. So as the mean and covariance update, the purpose is to generate smarter samples that eventually stem from the center of the distribution rather than wherever the previous sample was, because this essentially eliminates the possibility of accepting a sample in a low density region and then generating a bunch of random samples around that low density region and getting stuck and skewing the distribution to an area that it isn't supposed to fit. Another variation is called delayed rejection. So if a sample is rejected, the covariance matrix is tightened or scaled by some factor. So instead of if the covariance matrix being the identity, it might be the identity times 1e negative 3. And then it's resampled, which means the sample is generated closer with the tighter covariance. The sample is going to be closer to whatever the current sample is. And then it's going to be either accepted or rejected again. If it's accepted, then that would be the new sample. If it's rejected, that could either end the acceptance rejection process, or you can keep resampling as many times until you accept a sample. And the purpose of this is to increase the number of acceptances to make a distribution less sparse. Because for instance, if the way that the algorithm is set up, you're only accepting 5 or 6% of all your samples, that's just not acceptable. You want to be in the 30%, 40% range. And one of the ways of doing that, instead of manually hand tuning to find what the covariance matrix should be to get to that desired acceptance value, is to delay the rejection. And then another variation is to put the two together. You have the mean and covariance adapt, and you also delay the rejection. And the variation I used for this project was the standard adapt in Metropolis. So to put an example into a system that has been taught thoroughly in math classes, physics classes, and mechanical engineering and aerospace engineering classes, is what's called a mass spring damper system. And you can look at a rigid body that's moving through space and is attached to some dashpot with some dashpot coefficient and a spring with some spring constant. And let's say the parameters that we don't know are what the damping coefficient, what the spring constant are. And we're trying to figure that out. And looking at the ordinary differential equation that governs this rigid body through space, we can see both the damping constant and the spring constant are normalized by the mass. So let's say this is the mass we're trying, let's say these are the constants we're trying to find, what the mass normalized damping constant is and what the mass normalized spring constant is. So for the purpose of this, we know what the truth is because this is a well-studied system. We know exactly what it should, what the model should fit. So we can generate some synthetic data, or we can run the experiment. But for the purpose of this demonstration, synthetic data was generated, and we use a normalized spring constant of -2 and a normalized dashpot constant of -0.3. And the data was generated as shown. It was perturbed after the data was generated. It was perturbed with some noise of standard deviation 1. So these are going to be the initial states of our model. We're going to assume, for the sake of our model, that our prior for the parameters, in this case, our parameters, the unknowns, are the dashpot constant and the spring constant. We're going to assume these parameters are going to be Gaussian. We're going to assume with the distribution they're going to follow some kind of normal fit, and so because we know how to analyze that, that's a prior assumption that we can make and we can control. The next step is to calculate the likelihood. This is the belief of what the evidence is going to look like given our prior. And mathematically, this comes out to be a least squared errors algorithm. Y sub I here represents the actual data that we're getting, and these are our noisy perturbed data points. And M of X sub I comma theta is going to be the current iteration of the model given our current belief of the parameters. So each time we sample, the samples contain what we think the parameters are at that sample. So we're going to plug that in to the equation, generate some new data, see how far the data stems from the truth, square that, find the least squared error, and then divide by sigma squared, where sigma is the noise term. So where the data is generated with a lot of noise, the noise does get canceled out. But there are some optimization tactics we can use for Markov chain Monte Carlo. The first of which is called the Laplace approximation. What that does essentially is helps us find what's known as the map point. And the map point is a calculated way to determine what the center of the distribution is, the maxima a priori point, which helps us figure out where in the distribution we should start sampling to make sure we don't start in a low probability zone to ensure that we have the best chance of success. Burn-in removes the first 5%, 6%, X% of our samples. So if we do happen to start in a bad density zone and we're stuck in the beginning in a bad spot, then we start modeling the distribution properly. We get rid of those first 100,000, 2,000 data points, so that we just look at the rest of them. So the density and the distribution matches what it's supposed to. So these are the results from running the Markov chain Monte Carlo on that mass spring damper system. As you can see, the truth again is plotted in the middle, and here on the left side, the red represents all the samples, and on the right side, the green represents the velocity of all the samples. And what we can see is that the samples actually tend to show to match the truth. There is some level of uncertainty that's growing over time, and it's a pretty accurate fit. We can see that looking at the density or the distribution of samples in the bottom left, they are relatively close to -2 and -0.3, which is the truth of that system. And we can map some kind of credibility curves and confidence intervals to that as well. The sample traces in the bottom show the location of each individual sample as a function of sample number or over time, and it looks like white noise, which proves that the samples are being generated randomly, which is what we want to see. On the right side, this also proves that it's an autocorrelation graph that shows a lag between one sample and the next sample for the first 300 samples. And the lag essentially shows what the correlation is between one sample and the next, or from the first sample. So the first sample and the second sample have a 20% correlation. And by the time it gets close to the 20th or 30th sample, then we're already down to 0 correlation, and then it bounces up and down, fluctuates from there, which shows it's a pretty good sampling method. So the system works. This is really good to see. And now that we've fine-tuned this on a known system, we can start moving into the data at hand generated by Pepple. So they provided some time series data containing inputs and outputs for the model. The base model I created with the mass spring damper system had to be altered to take in inputs. And the inputs here were cathode current, and the outputs were anode voltage. And what we want to do is we were given thousands and thousands of data points in multiple different trajectories, and we wanted to train our model on a small subset and determine the unknown parameters, and then use our guess for the parameters on the rest of the data set to determine the accuracy of our fits, because we can always figure that out. We can see how close our guesses were to the rest of the data set, and then from there start generating predictions for how the thruster operates under different conditions, of course, with some level of uncertainty. So they provided a model, as mentioned before, with some delayed differential equations. That model is a work in progress and doesn't exactly fit the data, so that model had to be discarded. Instead, we had to construct the relationship by hand and then determine the parameters ourselves. So what we ended up working with was a feed-forward neural network that essentially takes the inputs and then passes them through a series of hidden layers with some state delay, and then ends up with the outputs. And our goal was to determine the weights of those nodes in the hidden layers. We achieved what's called a partial characterization and approximation of the parameters. This took a lot of hand tuning, as you can see on the right. It's still not even a perfect fit. The data provided is shown in blue, and the fit that we were able to generate is shown in orange. It doesn't on an overall level, I wasn't able to show the axes of the graph because the data itself is proprietary and classified, but on an overall scale, this is the same order of magnitude, so it's a pretty good fit. But the number of hidden layers can be increased. The number of nodes per layer can be increased. It is going to take a lot of time for it to run. It requires a lot of computational power, but overall, this is a decent fit, but needs a little bit of work. As mentioned previously, hand tuning was required to generate an appropriate model for the data. This started with using a polynomial approximation for the model itself. Once the rough delayed differential equation model was found to be not accurate, we tried with and without inputs, tried first order, second order, different combinations. That didn't seem to work at all. Then we moved to a feed-forward neural network. We tried different number of hidden layers, different number of nodes per layers. Finally settled on 2 to keep the computation and runtime short. Played around with the number of nodes, and future steps include refining this neural network model for the algorithm by adding more layers and widening the layers, refining the original delayed differential model that was provided so we can actually simulate the data itself to see what it should look like. The other thing we need to do is implement noise learning. So in the mass spring damper system, we knew what the noise was because we synthesized the data. In actual testing, we have no clue what the noise parameter is because it's just whatever the system noise is. So there's a way, using what's known as an inverse gamma prior, that we can learn what the noise is and then treat noise as one of the parameters and back that out. And yeah, I would really like to thank Professor Gordetsky for all his help throughout this project, Professor George for the data, and then the engineering program for all their support. Thank you.